So what I will do here is derive the equations of motion, or specifically the inviscid flow equations, the Euler equations, using a shell balance. So deriving Euler's equations using shell balance. Shell balance. So again, we're going to draw a control volume arbitrarily placed in the fluid. Okay. And we're going to start with the x momentum. And the law says that the rate of accumulation of momentum is equal to rate of momentum in minus rate of momentum out plus summation of forces. So for x momentum, that's mu, so the x momentum. So the units here are kilograms times meter per second. The rate of momentum accumulation is d by dt of that. So the units would be kilograms dot meter per second squared, just to keep the units in mind. Now the rate of accumulation of momentum in this control volume, so let's say this has distance delta x and then delta y and then delta z. So we're going to be doing this thing. So we will do x, y, and z. So this would be delta z and this would be delta y. The rate of accumulation of momentum, so accumulation would be delta x by delta y by delta z. That's the the volume of this small volume, times d rho u by dt. Okay. Now this is momentum per unit volume. That's mom per unit volume. Okay. Because that's what we're transporting. Okay. And we do it per unit volume, so you don't have to worry about the volume, right? So you just transport things per unit volume. You're not worried about this particular size of the volume, right? So this is kilograms per meter cubed times meter per second. Now multiplying by delta V, the total units of this thing, you can verify that this is meters cubed times kilograms per meter cubed times meter per second times 1/second. So that gives you kilogram per meter per second squared, and that's the rate of momentum. Okay. Now rate of momentum in, so we have a few things going on here. This is an advective motion. So in other words, if you think of momentum rho u, of the x momentum rho u, as a quantity that is being transported in the fluid, this rho u is going to be transported, so rho u will be transported by the velocity field. via advection. So that the x velocity, u, is going to transport rho u, v will also transport rho u, and w will also transport rho u. And the result here is that because u, v, and w are aligned in the different directions, but if you think of rho u as a scalar, but u, v, w as the velocity field, u is going to bring in rho u through the x faces, v is going to bring in rho u through the y faces, and w is going to bring in rho u through the z faces. So for example, what's coming in through this x face over here would just be u rho u. That's rho u being transported by the advective motion by the x velocity. And this is at location x. And we're going to say that it's going to come out from here, u rho u at x plus delta x. Same way, in the y direction, we have v rho u at y coming in, and v rho u at y plus delta y coming out. Now the units for this need to be adjusted because this is a flux through an area. So u rho u at x really needs to be multiplied by delta y times delta z. To verify the units, this is meter per second times kilograms per meter cubed times meters per second times meters squared. So that gives you meters cubed, and meters cubed go away. You get kilograms at meters per second squared, and that's the rate of momentum. Okay, and same thing in the z direction. You have w rho u at location z times delta x delta y, and what's coming out is also w rho u at z plus delta z times delta x delta y, etc. So in other words, the rate of momentum coming in is u rho u at x times delta y delta z plus, so we're summing up everything that's coming in, plus v rho u at y, okay, times delta x delta z. So v rho u y delta x delta z over here. Same thing here, delta x delta z. Okay. Plus w rho u at location z, okay, times delta x delta y. Okay. And then rate of momentum out, same thing, is u rho u at x plus delta x delta y delta z plus v rho u at y plus delta y delta x delta z plus w rho u at z plus delta z delta x delta y. It is important to recognize what is transporting what. So in this case, it's the velocity field u, v, w transporting the x momentum component. Okay? And finally, in terms of forces, we said we're only going to consider gravity and pressure for now. So the force of gravity, that's simply going to be rho gx delta x delta y delta z. Okay, and verify the units. Kilogram per meter cubed goes away, and you have meters per second squared, so you get kilograms of meter per second squared. All units are consistent. And finally, for the pressure, so for the pressure, in this case, the pressure force is going to act in the x direction. So we have this situation. On the x face, we have a force p at x, and on this x plus delta x face we have a minus px plus delta x. So the net force in the x direction is, and you have to multiply by the area, it's px minus px plus delta x times delta y delta z. Okay. So next all we have to do is put all of these things together. That gives us the rate of accumulation of momentum, d rho u by dt times delta x, delta y, delta z, equals momentum in, so that was u rho u at x times delta y, delta z, plus v rho u at y times delta x, delta z, plus w rho u at z times delta x, delta y, minus u rho u at x plus delta x, delta y, delta z, minus v rho u y plus delta y times delta x, delta z, minus, so remember rate in minus rate of momentum out, w rho u at z plus delta z times delta x, delta y, and then we have gravity, or let's start with pressure, plus px minus px plus delta x times delta y, delta z, finally gravity, plus rho gx, delta x, delta y, delta z. Now divide by delta x, delta y, delta z, and arrange terms. So I'm going to combine all the convective momentum terms, whatever is being transported by convection, and we will have d rho u by dt equal minus u rho u at x plus delta x minus u rho u at x over delta x. So all I did was take the negative sign out so that I get what looks like a derivative, okay, minus v rho u at y plus delta y minus v rho u at y over delta y. You can see where we're headed, minus w rho u at z plus delta z minus w rho u at z over delta z, minus p at x plus delta x minus p at x over delta x plus rho g, and then in the limit as delta x, delta y, delta z approach 0, we recover the x component of the Euler momentum equations. So d rho u by dt equals minus partial u rho u by dx minus partial v rho u by dy minus partial w rho u by dz minus dp by dx plus rho gx. Okay. Now you can write this in vector form if you want. Just the advective derivatives can be written as div u rho u. Okay. A similar thing applies for the y momentum and the z momentum equations, and you get the same exact thing doing the shell balance.